Euclid's Elements, Book 3, Proposition 2. If on the circumference of a circle, 2 points be taken at random, the straight line joining those 2 points will fall within the circle. So here's our given. We have a circle, and we can just pick any 2 points at random. Here's A, here's B. And if we join them with a straight line, this prop is saying that it will fall. The straight line joining those 2 points will fall within the circle. This is a proof by contradiction, so we are going to start by assuming that this is false. So let's assume that the straight line joining AB, 2 points chosen at random on a circumference, doesn't fall within the circle. Let's say it falls outside the circle somehow. So this is going to be our assumption, that line AB falls outside the circle. So how would that look? Well, it might look like this perhaps. So we're saying somehow that we're going to draw a straight line and it's not going to fall within the circle. Let's say it falls somehow outside the circle. Now I know it doesn't look like a straight line, but we don't judge by appearances. We're simply going to show this leads to a logical contradiction. So the first thing Euclid does is he finds the center of the circle. So we're going to use Book 3, Prop 1, and find the center of our circle and let it be C. So we're going to find C. And now we can connect CA and CB. We can pick another point at random. Let's call this D. And so let's join CD and then extend this through to E. So what we can immediately notice is that since CA and CD and CB are all coming from the center to the circumference, they're all radii, and all radii are equal. So radii are equal. Therefore, we know that CA is equal to CD, which is equal to CB. Now let's look at triangle ACB. In triangle ACB, we have 2 sides that are equal to each other. So it's an isosceles triangle. And we know in an isosceles triangle, according to Prop 5, Book 1, that the base angles of an isosceles triangle are equal. So we know that this angle here is equal to this base angle here. So let's call this angle 1, and we'll call this angle 2. So angle 1 is equal to angle 2, base angles of our triangle ABC. Now let's look at this triangle ACE. Okay, in triangle ACE, we have one of these lines, this straight line extended. So what we have here, and redraw this a little bit, okay, we have A, C, and E going over here to B. So it makes this angle here, right? This is an angle created by one line of the triangle being extended. And so this is called an external angle. And we know from Prop 16 of Book 1 that the external angle is always greater than the opposite and interior angles. So the external angle, the angle here at E, which we'll label, let's label this angle 3. The external angle, angle 3, has to be greater than the opposite angle here, which would be angle 1. So angle 3 is greater than angle 1, the opposite interior angle. But we know angle 1 is equal to angle 2. Therefore, angle 3 has to be greater than angle 2. Which brings us to proposition 19 of Book 1, which says if we have a triangle, so now look at triangle CEB. Okay, in triangle CEB, we have one angle greater than another angle. Prop 19 says the greater angle is subtended by the greater side. And so the side subtending the greater angle is CB. Therefore, CB has to be greater than CE, the side subtending angle 2. But remember, CB is equal to CD. So we can say CD has to be greater than CE. But wait a minute, let's take a look at what we're saying. We're saying that this line, CD, has to be greater than this line, CE. We're saying that the part of the line has to be greater than the whole of the line. This is the part, and this is the whole, and we're saying that the part is greater than the whole, which is an obvious contradiction of common notion 5 that says that the whole is always greater than the part, that the part is always less than the whole. So now we've concluded the opposite of this. We've concluded something absurd. And so we have to reject this as absurd. And therefore we have to reject the assumption that gave rise to this absurdity, and that was assuming that AB falls outside the circle. Therefore, AB does not fall outside the circle. Well, what about if AB fell on the circle? What if it fell on the circumference? Does that solve our problem? Nope. We can use the same logic to show that it can't fall in the circle or on the circumference, which is on the circle. And we get the same, because we get the same absurdity. The angle here at D, which is now, we'll use our angle, a new angle 3. Our angle here at D becomes the external angle, and so it's bigger than the opposite interior angle. And since this is equal to this is greater than this, therefore this side must be greater than this side, but they're equal. So it can't be both greater than this and equal to this at the same time, therefore it leads to another circle. So it can't fall outside the circle. It can't fall on the circle. Therefore, the only place it can fall is inside the circle. And that's what we're trying to prove, that any 2 points taken at random on a circumference, if you join them with a straight line, that line will fall inside the circle. And since we've proved that, we conclude with QED.